Chapter 14, Part 2 of Volume 2 of Airplane Flying Handbook, FAA-H-8083-3A. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Airplane Flying Handbook by the FAA. Transition to turbopropeller-powered airplanes. Part 2. Reverse thrust and beta range operations. The thrust that a propeller provides is a function of the angle of attack at which the air strikes the blades and the speed at which this occurs. The angle of attack varies with the pitch angle of the propeller. So-called flat pitch is the blade position offering minimum resistance to rotation and no net thrust for moving the airplane. Forward pitch produces forward thrust, higher pitch angles being required at higher airplane speeds. The feathered position is the highest pitch angle obtainable. See Figure 14-8. The feathered position produces no forward thrust. The propeller is generally placed in feather only in case of in-flight engine failure to minimize drag and prevent the air from using the propeller as a turbine. In the reverse pitch position, the engine/propeller turns in the same direction as in the normal forward pitch position, but the propeller blade angle is positioned to the other side of flat pitch. See Figure 14-8. In reverse pitch, air is pushed away from the airplane rather than being drawn over it. Reverse pitch results in braking action rather than forward thrust of the airplane. It is used for backing away from obstacles when taxiing, controlling taxi speed, or to aid in bringing the airplane to a stop during the landing roll. Reverse pitch does not mean reverse rotation of the engine. The engine delivers power just the same, no matter which side of flat pitch the propeller blades are positioned. With a turboprop engine, in order to obtain enough power for flight, the power lever is placed somewhere between flight idle, in some engines referred to as high idle, and maximum. The power lever directs signals to a fuel control unit to manually select fuel. The propeller governor selects the propeller pitch needed to keep the propeller/engine on speed. This is referred to as the propeller governing or alpha mode of operation. When positioned aft of flight idle, however, the power lever directly controls propeller blade angle. This is known as the beta range of operation. The beta range of operation consists of power lever positions from flight idle to maximum reverse. Beginning at power lever positions just aft of flight idle, propeller blade pitch angles become progressively flatter with aft movement of the power lever until they go beyond maximum flat pitch and into negative pitch, resulting in reverse thrust. While in a fixed shaft, constant speed engine, the engine speed remains largely unchanged as the propeller blade angles achieve their negative values. On the split shaft PT6 engine, as the negative 5-degree position is reached, further aft movement of the power lever will also result in a progressive increase in engine N1 RPM, until a maximum value of about negative 11 degrees of blade angle and 85% N1 are achieved. Operating in the beta range and/or with reverse thrust requires specific techniques and procedures depending on the particular airplane make and model. There are also specific engine parameters and limitations for operations within this area that must be adhered to. It is essential that a pilot transitioning to turboprop airplanes become knowledgeable and proficient in these areas, which are unique to turbine engine-powered airplanes. Turboprop airplane electrical systems. The typical turboprop airplane electrical system is a 28-volt direct current DC system, which receives power from one or more batteries and a starter/generator for each engine. The batteries may either be of the lead-acid type, commonly used on piston-powered airplanes, or they may be of the nickel-cadmium NiCad type. The NiCad battery differs from the lead-acid type in that its output remains at relatively high power levels for longer periods of time. When the NiCad battery is depleted, however, its voltage drops off very suddenly. When this occurs, its ability to turn the compressor for engine start is greatly diminished, and the possibility of engine damage due to a hot start increases. Therefore, it is essential to check the battery's condition before every engine start. Compared to lead-acid batteries, high-performance NiCad batteries can be recharged very quickly, but the faster the battery is recharged, the more heat it produces. Therefore, NiCad battery-equipped airplanes are fitted with battery overheat annunciator lights, signifying maximum safe and critical temperature thresholds. The DC generators used in turboprop airplanes double as starter motors and are called starter/generators. The starter/generator uses electrical power to produce mechanical torque to start the engine, and then uses the engine's mechanical torque to produce electrical power after the engine is running. Some of the DC power produced is changed to 28-volt 400-cycle alternating current AC power for certain avionic, lighting, and indicator synchronization functions. This is accomplished by an electrical component called an inverter. The distribution of DC and AC power throughout the system is accomplished through the use of power distribution buses. These buses, as they are called, are actually common terminals from which individual electrical circuits get their power. See Figure 14-9. Buses are usually named for what they power. Avionics bus, for example, or for where they get their power. Right generator bus, battery bus. The distribution of DC and AC power is often divided into functional groups, buses, that give priority to certain equipment during normal and emergency operations. Main buses serve most of the airplane's electrical equipment. Essential buses feed power to equipment having top priority. See Figure 14-10. Multi-engine turboprop airplanes normally have several power sources, a battery, and at least one generator per engine. The electrical systems are usually designed so that any bus can be energized by any of the power sources. For example, a typical system might have a right and left generator buses powered normally by the right and left engine-driven generators. These buses will be connected by a normally open switch, which isolates them from each other. If one generator fails, power will be lost to its bus, but power can be restored to that bus by closing a bus tie switch. Closing this switch connects the buses and allows the operating generator to power both. Power distribution buses are protected from short circuits and other malfunctions by a type of fuse called a current limiter. In the case of excessive current supplied by any power source, the current limiter will open the circuit and thereby isolate that power source and allow the affected bus to become separated from the system. The other buses will continue to operate normally. Individual electrical components are connected to the buses through circuit breakers. A circuit breaker is a device which opens an electrical circuit when an excess amount of current flows. Operational considerations. As previously stated, a turboprop airplane flies just like any other piston-engine airplane of comparable size and weight. It is in the operation of the engines and airplane systems that makes a turboprop airplane different from its piston-engine counterpart. Pilot errors in engine and/or systems operation are the most common cause of aircraft damage or mishap. The time of maximum vulnerability to pilot error in any gas turbine engine is during the engine start sequence. Turbine engines are extremely heat sensitive. They cannot tolerate an over-temperature condition for more than a very few seconds without serious damage being done. Engine temperatures get hotter during starting than at any other time. Thus, turbine engines have minimum rotational speeds for introducing fuel into the combustion chambers during startup. Hypervigilant temperature and acceleration monitoring on the part of the pilot remain crucial until the engine is running at a stable speed. Successful engine starting depends on assuring the correct minimum battery voltage before initiating start, or employing a ground power unit, GPU, of adequate output. After fuel is introduced to the combustion chamber during the start sequence, light off and its associated heat rise occur very quickly. Engine temperatures may approach the maximum in a matter of 2 or 3 seconds before the engine stabilizes and temperatures fall into the normal operating range. During this time, the pilot must watch for any tendency of the temperatures to exceed limitations and be prepared to cut off fuel to the engine. An engine tendency to exceed maximum starting temperature limits is termed a hot start. The temperature rise may be preceded by unusually high initial fuel flow, which may be the first indication the pilot has that the engine start is not proceeding normally. Serious engine damage will occur if the hot start is allowed to continue. A condition where the engine is accelerating more slowly than normal is termed a hung start or false start. During a hung start/false start, the engine may stabilize at an engine RPM that is not high enough for the engine to continue to run without help from the starter. This is usually the result of low battery power or the starter not turning the engine fast enough for it to start properly. Takeoffs in turboprop airplanes are not made by automatically pushing the power lever full forward to the stops. Depending on conditions, takeoff power may be limited by either torque or by engine temperature. Normally, the power lever position on takeoff will be somewhat aft of full forward. Takeoff and departure in a turboprop airplane, especially a twin-engine cabin-class airplane, should be accomplished in accordance with a standard takeoff and departure profile developed for the particular make and model. See Figure 14-11. The takeoff and departure profile should be in accordance with the airplane manufacturer's recommended procedures as outlined in the FAA-approved Airplane Flight Manual and/or the Pilot's Operating Handbook, AFM/POH. The increased complexity of turboprop airplanes makes the standardization of procedures a necessity for safe and efficient operation. The transitioning pilot should review the profile procedures before each takeoff to form a mental picture of the takeoff and departure process. For any given high-horsepower operation, the pilot can expect that the engine temperature will climb as altitude increases at a constant power. On a warm or hot day, maximum temperature limits may be reached at a rather low altitude, making it impossible to maintain high horsepower to higher altitudes. Also, the engine's compressor section has to work harder with decreased air density. Power capability is reduced by high-density altitude, and power use may have to be modulated to keep engine temperature within limits. In a turboprop airplane, the pilot can close the throttle or throttles at any time, without concern for cooling the engine too rapidly. Consequently, rapid descents with the propellers in low pitch can be dramatically steep. Like takeoffs and departures, approach and landing should be accomplished in accordance with a standard approach and landing profile. See Figure 14-12. A stabilized approach is an essential part of the approach and landing process. In a stabilized approach, the airplane, depending on design and type, is placed in a stabilized descent on a glide path ranging from 2.5 to 3.5 degrees. The speed is stabilized at some reference from the AFM/POH, usually 1.25 to 1.30 times the stall speed in approach configuration. The descent rate is stabilized from 500 feet per minute to 700 feet per minute until the landing flare. Landing some turboprop airplanes, as well as some piston twins, can result in a hard, premature touchdown if the engines are idled too soon. This is because large propellers spinning rapidly in low pitch create considerable drag. In such airplanes, it may be preferable to maintain power throughout the landing flare and touchdown. Once firmly on the ground, propeller beta range operation will dramatically reduce the need for braking in comparison to piston airplanes of similar weights. Training considerations. The medium and high altitudes at which turboprop airplanes are flown provide an entirely different environment in terms of regulatory requirements, airspace structure, physiological requirements, and even meteorology. The pilot transitioning to turboprop airplanes, particularly those who are not familiar with operations in the high/medium altitude environment, should approach turboprop transition training with this in mind. Thorough ground training should cover all aspects of high/medium altitude flight, including the flight environment, weather, flight planning and navigation, physiological aspects of high-altitude flight, oxygen and pressurization system operation, and high-altitude emergencies. Flight training should prepare the pilot to demonstrate a comprehensive knowledge of airplane performance, systems, emergency procedures, and operating limitations, along with a high degree of proficiency in performing all flight maneuvers and in-flight emergency procedures. The training outline below covers the minimum information needed by pilots to operate safely at high altitudes. A. Ground training. 1. The high-altitude flight environment. A. Airspace. B. Title 14 of the Code of Federal Regulations, 14 CFR, Section 91.211, Requirements for use of supplemental oxygen. 2. Weather. A. The atmosphere. B. Winds and clear air turbulence. C. Icing. 3. Flight planning and navigation. A. Flight planning. B. Weather charts. C. Navigation. D. Navaids. 4. Physiological training. A. Respiration. B. Hypoxia. C. Effects of prolonged oxygen use. D. Decompression sickness. E. Vision. F. Altitude chamber, optional. 5. High-altitude systems and components. A. Oxygen and oxygen equipment. B. Pressurization systems. C. High-altitude components. 6. Aerodynamics and performance factors. A. Acceleration. B. G-forces. C. Mach tuck and Mach critical, turbojet airplanes. 7. Emergencies. A. Decompression. B. Donning of oxygen masks. C. Failure of oxygen mask or complete loss of oxygen supply/system. D. In-flight fire. E. Flight into severe turbulence or thunderstorms. B. Flight training. 1. Pre-flight briefing. 2. Pre-flight planning. A. Weather briefing and considerations. B. Course plotting. C. Airplane flight manual. D. Flight plan. 3. Pre-flight inspection. A. Functional test of oxygen system, including the verification of supply and pressure, regulator operation, oxygen flow, mask fit, and cockpit and air traffic control, ATC communication using mask microphones. 4. Engine start procedures, run-up, takeoff, and initial climb. 5. Climb to high altitude and normal cruise operations while operating above 25,000 feet MSL. 6. Emergencies. A. Simulated rapid decompression, including the immediate donning of oxygen masks. B. Emergency descent. 7. Planned descents. 8. Shutdown procedures. 9. Post-flight discussion. End of Chapter 14, Part 2.